Security Plus, Cryptography Algorithms and Protocols. The year was 1914. It's the Battle of Tannenberg, a decisive German victory of World War I. Tannenberg, a town in East Prussia, was supposed to be invaded by two Russian armies. Here's the story, according to historian David Kahn. Russian communications were woefully inadequate. Their communications lay naked to the enemy. The general inefficiency that crippled the Russian mobilization had fouled up distribution of the new military cipher and its keys. Before a fortnight had passed, Russian signalmen were no longer even trying to encrypt messages. They were just passing them over the radio in the clear. Almost 100,000 Russians were taken prisoner. An estimated 30,000 were dead or missing. The Russian Second Army had ceased to exist. Hoffmann, the architect of the victory, acknowledged its real cause. We had an ally that I can only talk about after it's all over. We knew all the enemy's plans. The Russians sent out their wireless in clear. The case was clear-cut. Interception of unenciphered communications had awarded the Germans their triumph. Tannenberg, which gave Russia the first push on her long slide into ruin and revolution, was the first battle in the history of the world to be decided by cryptographic failure. In Cryptography Part 2, we're going to continue our discussion looking at cryptography algorithms and protocols. We'll look at hashing concepts and protocols that use hashing. We'll revisit a bevy of encryption algorithms you need to know about for the Security Plus exam. Then we'll also explore other additional protocols that use cryptographic techniques, things like SSL-TLS, S-MIME, PPTP, HTTPS and SHTTP, L2TP, IPsec, and SSH. As we say in Texas, more acronyms than you can shake a stick at. Hashing is often used to secure passwords on network devices. Hashing is often used, let's say, in authentication protocols like CHAP, for example. It can also be used to provide data integrity by creating a hash, appending it to data, and sending that over the wire. So hashing is a mechanism that's used primarily for what we call data integrity assurance. It's based on a one-way mathematical functions that are relatively easy to compute, but they're very, very difficult to reverse. For example, imagine if you had a jar full of marbles and you toss that jar onto the floor. Think of the difficulty it would be to compile all those marbles back into the jar in the same exact position that they were before you dropped the jar. Very difficult to do. Or maybe think about this, grinding coffee, okay? It's easy to grind coffee beans, but consider trying to put those tiny granules back together to rebuild the original beans in their original order in the bag. So you can see what we have here is we have our data, our original data of arbitrary length. It could be an email message, for example, or it could be a text file. You're going to send the data through this mathematical hash function. The result of the hash function is going to be a fixed length hash known as a digest, okay? A digest or a fingerprint. That's the result here, okay? You know, hashing is a lot like the calculation of a cyclic redundancy check, a CRC checksum, that's done just in basic layer 2 communications with frames, for example, but it's a much stronger cryptographic process. And as I mentioned, hashing is used for a wide variety of different purposes. It can be used to scramble passwords. Okay, I put scramble PW here. Scramble passwords. It can be used with the CHAP protocol for authenticating two devices or two users. It can also be used to apply data integrity to a communication message by simply appending the hash to the original message and then once it gets to the receiver, the same mathematical function is performed against that hash, and if just 1, 0, or 1 is changed, the receiver knows I'm not going to accept this message. It doesn't have the integrity. It's been modified in transit. So hashing is also a very important cryptographic function that's used for data integrity. Let me clean up my screen here so I can elaborate a little bit. Let's say we've got hashing and we want to use this to authenticate a user to, let's say, some type of server system using CHAP, which is the Challenge Handshake Authentication Protocol, which is commonly used with ISPs. It's also used in a Microsoft environment as well with an RAS server. It's an authentication scheme that is used by point-to-point protocol servers to validate the identity of remote clients. And CHAP happens to use this one-way hash function I've been talking about. Now remember, it's almost impossible to reverse a one-way hash function back to its original text. In our case here, the text is our password or our credentials. Let's say username and password. The good thing about CHAP is these credentials are not sent over the wire. During the login process, the user supplies an account and a password, and the hashing algorithm generates a one-way hash, something similar to that. Once it's received over here at the server side, the algorithm compares this hash to the hash stored on its system, and if the hashes are the same, the algorithm assumes that the user or the system supplied the right credentials. Remember, passing the password or the credentials to the algorithm results in this hash. The hash is not the encrypted password. It's the result of the algorithm. And the strength of the hash is that the hash value can only be recreated using the original user and password information. It's virtually impossible to retrieve the original information from the hash. And this is what makes hashes perfect for doing things like encoding passwords for storage, especially on, let's say, Cisco routers, for example, that use the MD5, Message Digest 5 protocol, as just an example. Now, this doesn't mean that hashing is impervious to being cracked. For example, there's a program called Rainbow Crack that's a compilation of a bunch of hashes, and this provides crackers or malicious hackers with a list that they can use to attempt to match hashes that they capture with sniffers. So you can have these database of hashes which are basically generated from common hashing protocols and common dictionary passwords, and you can use this against this. So again, there are vulnerabilities with hashing. For example, if you're going to save a bunch of passwords on a Cisco router, let's say, which is very common, you can run a command on that router called service space password encryption. And what it does is, let me go ahead and finish out the command here. What service password encryption does is it hashes all of the existing passwords on that particular system, the ones that admins use to log on and people who used for telnet sessions and things like that, when they log on. It's saved in the router's configuration file, and it will keep hashing any passwords. The problem is this methodology is not as strong or as safe as MD5 that I mentioned, which is used when we create what's called an enable secret command on our router or switch or multi-layer switch or firewall, and it's vulnerable to tools like Rainbow Crack or Cain and Abel is another one as well. So we want to keep that in mind. Now, earlier on I mentioned the SNMP protocol, which is used for monitoring and control and management of a network environment. Well, the new version of SNMP, SNMP version 3, provides not only encryption, but it provides authentication of the SNMP devices, and it uses a hashed message authentication code, or HMAC, with MD5. or SHA protocol, which is the secure hash algorithm. And this is used to basically authenticate the devices. Let me give you a heads up. You might want to outline this slide. I'm not going to write down everything that I say here as we go through these hashing algorithms. Now, SHA stands for Secure Hash Algorithm, and it's a set of cryptographic hash functions. It was designed by the National Security Agency, and it is published in the NIST as a standard. NIST is the National Institute of Standards and Technology. There's 5 algorithms. You've got SHA-1, SHA-224, SHA-256, SHA-384, and SHA-512. These are typically all grouped up as SHA-2. Now, SHA-1, which is the one we see most commonly, gives us a message digest that is 160 bits in length. It's the best and most well-established of the existing SHA hash functions, and it's widely deployed in a wide variety of security applications and protocols, both wired and wireless. A new hash function, which is SHA-3, is going to be made official probably in the year 2012. Now, it's not important to understand how the mathematics of SHA works, this cryptographic hash function, but it's used in a wide variety of protocols that we're going to be talking about here in a second. It's used in SSL and TLS. SHA-1 is also used in PGP, pretty good privacy. We'll be looking at that. Secure Shell, it's used in Secure Shell. It's used in SMIME, which we're going to define here in a bit, and it's also used in IPsec. Now, all of these protocols can also use MD5 as well. As a matter of fact, MD5 and SHA-1 are both kind of ancestors, or descendants, I should say, of the MD4 protocol, which is no longer that secure. Let's go and talk about MD5. MD5 stands for Message Digest Algorithm 5. It's widely used, but it's not completely secure, so it does have limitations. It uses a 128-bit hash value as opposed to the 160-bit of SHA-1. Therefore, SHA-1 is considered more secure than MD5. MD5 was designed by Ron Rivest, R-I-V-E-S-T, in 1991. He's a very important and very influential person in the process. MD5 digests are used throughout the world in software to provide assurance that the transferred file has been delivered intact. So MD5 is often used for integrity mechanisms. For example, file servers will often provide a pre-computed MD5 checksum for the files. Then the user can compare the checksum to the downloaded file. Unix uses MD5 utilities in their distribution packages as well. MD5 is widely used to store encrypted or hashed passwords, as I talked about widely, for example, in the Cisco environment. Now, I've got Landman written down here, and I'm only mentioning this because it's one of the objectives on the Security Plus exam, although Landman is obsolete, so I'm not really quite sure why they're including it. I would highly doubt that you're going to see it on the test, but it's an obsolete authentication protocol that was used historically in Microsoft Windows, and it was used before the implementation of Windows NT. So this is pre-NT technology. So I guess it's here because they're talking about the Landman hash, the LM hash, or the LAN manager hash that was used in old Windows versions to store user passwords that were fewer than 15 characters long. This type of hash was the only encryption used in Microsoft's LAN manager. As a matter of fact, it's so legacy that in Windows Vista, it has to be manually enabled to be used. So it's a block cipher that's based on DES, but it can be easily cracked, for example, with that Cain Enable program. Now, NTLM, or NT LAN Manager, is a Microsoft authentication protocol that's used with the SMB or Server Message Block protocol. Microsoft's recently replaced that with what we call CIFS. And this really relates to Microsoft's version of CHAP, MS CHAP. I mentioned CHAP to you earlier, how the process that CHAP goes through. Microsoft has their own iteration, and they use it for authentication with their remote access protocols. There's an MS CHAP version 1 and an MS CHAP version 2. Both these protocols are widespread, but they do have weaknesses built into them. They do use that challenge response process that we talked about, and they hash the credentials. NTLM version 2 was introduced in Windows NT Service Pack 4, and that's the one that you're going to see used most often. However, in most modern Microsoft implementations, you're going to do away with this authentication protocol, and you're going to be using Kerberos, which was designed by MIT. This is the preferred authentication protocol for Windows 2000, 2003, and 2008 Active Directory domains. But NTLM is still used when clients authenticate to servers with an IP address, or if a client's authenticating to a server that belongs to a different Active Directory forest, or a server that doesn't belong to a domain at all. It'll be used if there's no Active Directory domain. For example, there's a work group or a peer-to-peer network. Or sometimes NTLM is still used if a firewall restricts the ports that Kerberos needs. So these are 4 very common hashing algorithms or protocols that use hashing. Or really 3, SHA-MD5 and NTLM, which is rapidly being replaced by Kerberos. So one last final word on hashing. Again, it's used to generate one-time and one-way responses to challenges in authentication protocols like CHAP, for example. As we just mentioned, it's used in Microsoft NT domain environments. It's also used with Extensible Authentication Protocol, EAP, which is used in a wired and wireless environment, specifically with EAP MD5. Hashing can also be used to provide data integrity with file integrity checkers for digitally signed contracts and public key infrastructure certificates. We're going to talk about PKI in depth in the next nugget. Also, it can provide proof of authenticity when it's used with symmetric secret authentication keys, such as in an IPsec environment. Routing protocols also use it to authenticate routers to one another. Hashing is used there as well. So lots of applications for hashing. Okay, let's go ahead and continue our discussion, our survey of encryption algorithms, as we look at DES and triple DES, also referred to as DES and triple DES. DES is a cipher that's been around since, the mid-70s, and it's been really popular globally. There were some rumors out there that the National Security Agency, NSA, had built some backdoors into it. That was something that was kind of advertised. It has a relatively short key length compared to other protocols, so it's been highly scrutinized, and it's been subject to a lot of cryptanalysis. As a matter of fact, it's now considered insecure, DES. A couple of reasons. Number one, it's got a 56-bit key size, which is too small, and I think back in 1999, somebody cracked it in like 22 hours and some change. So the newer version, which is considered secure, is triple DES, and that is theoretically the more secure form of DES. You shouldn't probably use DES in your environment. You should use triple DES, or as we're going to talk about down here, what superseded that is the AES protocol. DES was designed by IBM, and it's still very popular. Triple DES, or triple DES, has been approved by NIST through the year 2030 for sensitive government information. Earlier I mentioned RSA, and RSA is an algorithm that's used specifically for public key cryptography or the public key infrastructure. Again, we're going to get into that in greater detail in the next nugget, but it was considered the first algorithm suitable for digital signatures as well as encryption. So it was a huge advancement in public key cryptography. It's widely used in electronic commerce protocols. And because it uses pretty long keys and up-to-date implementations, it's considered a very good solution for the Internet. PGP, no, it's not plasma gasification process. It's the pretty good privacy protocol. PGP is actually an application that provides cryptographic privacy and authentication, two of the things we talked about as being so important for cryptography. PGP can also use for signing digital signatures. Remember, when we talk about signing, we can sign off on a user's identity, we can sign off on an application, we can sign device drivers, we can sign hardware, as I've mentioned as well. It's used a lot to encrypt and decrypt emails to increase email communication security. It was created by Philip Zimmermann in 1991, and it's an open standard, so it basically follows the open PGP standard. Like RSA, PGP uses public key cryptography, which means it's an asymmetric solution with private keys and public keys. It also supports message authentication and integrity checking. To give us integrity, it computes a hash or a message digest from the plain text, and then it creates a digital signature from that hash using the sender's private keys. The newest version of PGP is PGP3, and it's still widely used, especially in the Linux and Unix environment. Another public key cryptography methodology is elliptic curve cryptography. I've got elliptic curve written here. It's also known as ECC, and I don't know how much your algebra background is, but it's based on algebraic structure of elliptic curves over finite fields, blah, 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 as far as I'm concerned. So the Diffie-Hellman protocol for exchanging private keys will also use elliptic curve cryptography. As a matter of fact, Diffie-Hellman group number 7 uses this key exchange method. This is designed for low-powered hosts like handheld devices and PDA. So you often see elliptic curve cryptography used with handheld devices. As I mentioned, AES is the Advanced Encryption Standard. It's really the de facto standard recommended by the U.S. government. It has replaced DES and triple DES in most implementations. It is a different type of protocol. It uses a substitution permutation method. It's not like DES or triple DES. AES is fast. It's fast in hardware. It's fast in software. Doesn't use a lot of memory. It's easy to implement, and it's deployed on a large scale. As of 2006, AES became the most popular algorithm to be used in symmetric key cryptography. So you see it in almost all encryption packages. It runs on all different types of platforms, C++, Java, all other languages. It can be used in archiving and compression tools like WinZip and PKZip. It's used for disk encryption as well as full disk encryption. OpenSSL, secure sockets layering, includes AES support. You'll see it in secure FTP. The list goes on and on. It's one of your options now in an IPsec implementation for data confidentiality. So the de facto standard now is AES, and of course the 256-bit version, AES 256, representing a 256-bit key length. Last but not least, we have the cryptographic method of a one-time pad, or it's also referred to as OTP. OTP is an encryption algorithm where our original plain text gets grouped up with a pad or a random key that's as long as the plain text, and it's only used one time. This has literally been around since like the early 1900s. So the concept is very well established. I think it was derived from some cipher called the Vernam cipher that some dude invented quite a while ago. It's used for perfect secrecy, and by the way, the guy who established it was named Claude Shannon. Very proud of him, of course. We share the same last name. I don't know if we're related, but one-time pad's been around for a long time. Okay, next we're going to look at a variety of additional protocols that use varying degrees of cryptography. The first we're going to look at is SSL-TLS. Now, the Security Plus exam, they separate these into kind of two different protocols, but understand that TLS, or Transport Layer Security, is actually the successor to Secure Sockets Layer, SSL. So SSL and TLS are kind of brother and sister or cousins or whatever. These are cryptographic protocols that are basically used to provide secure communications over untrusted networks like the internet, for things like faxing over the internet, for email, instant messaging, web browsing, and other data transfers. Now, there are some slight things that are different between SSL and TLS, but they're essentially the same protocols, and they're client-server protocols. So we're going to focus here on TLS because this is the one that's being used most of all today. For example, in your new browser, your new IE browser, you're using TLS. It allows your applications to talk over the network to prevent eavesdropping, to prevent tampering, and forgery of messages. It provides endpoint authentication and privacy using cryptography. There's really three phases to TLS. First of all, you're going to have a peer negotiation process for support of different algorithms, kind of like setting up a secure channel. Second, you're going to have a key exchange and authentication process. And then thirdly, TLS will do a symmetric cipher encryption and message authentication. So in phase one, they're going to negotiate, the client and server that is, or they're going to negotiate what are called cipher suites to determine the ciphers to be used, the key exchange process, and the authentication algorithms, as well as the message authentication codes, or the MACs, which are done through a hashing process. The key exchange and authentication algorithms are typically going to be public key algorithms, or you might use what's called TLS pre-shared keys. Typical algorithms that are used in SSL TLS are things like RSA, Diffie-Hellman, for example, and pre-shared key. They're used for the key exchange process. For authentication, typically you'll use RSA, or maybe another protocol the government uses called DSA. The symmetric ciphers, or the symmetric encryption programs, RC4, which we've talked about, Triple DES, AES, probably the most popular. Sometimes DES, but typically you'll also see IDEA used as well. Those are our symmetric keys, ciphers that are used. For the hashing function, for the cryptographic hashing that's done, remember as part of that negotiation process, you'll use HMAC, which is our message authentication code, HMAC MD5, or the stronger HMAC SHA, which we know is stronger than MD5. S-MIME is an open standard for public key encryption. It's also used to sign or digitally sign email that's been encapsulated in the MIME protocol. MIME is the multi-purpose internet mail extensions, and of course S-MIME being the secure version of that. This was developed by these people, okay, RSA Data Security, the ones that created the RSA protocol. And basically, S-MIME provides cryptographic security for email applications. It provides authentication, message integrity, and non-repudiation of the origin. It also provides privacy and data security with encryption. So S-MIME really provides all of the triad plus non-repudiation. S-MIME is built into all of the modern email software as well as modern browsers, and is built in, and there's built-in interoperability between all of them. S-MIME is kind of a public key infrastructure technology in that it uses either individual keys or certificates from a certificate authority, either one that's inside the organization or a public CA, like let's say VeriSign or Thought, someone like that. Let me just jot those down. VeriSign or Thought. So when you see SMIME, think secure email. Point-to-point tunneling protocol works with point-to-point protocol, okay? It operates by sending a regular PPP session to its peer within the generic routing encapsulation GRE protocol. So point-to-point tunneling protocol is basically PPP in a GRE tunnel. PPTP does the actual tunneling for virtual private networks. But the connections themselves are typically authenticated with Microsoft's MS Chat version 2 or often with EAP, Extensible Authentication Protocol, TLS. So here's TLS again, returning to the picture. In a Microsoft environment, the VPN traffic can also be encrypted. Okay, this is authentication, but the encryption of traffic in a Microsoft PPTP environment uses Microsoft's MPPE, which is the Microsoft Point-to-Point Encryption Protocol, and that's defined, by the way, in RFC number 3078, in case you want to take a look at that one. PPTP was the first VPN protocol supported by Microsoft's dial-up networking. Every release of Windows since Windows 95 Release 2 have been bundled with the PPTP client. It's heavily used in Microsoft Windows Server's RRAS, Routing and Remote Access Service. And even recently, you're starting to see Linux distributions and Mac OS X bundled with PPTP clients. HTTPS is Hypertext Transfer Protocol over Secure Socket Layer, okay, or SSL up here, and it's a mechanism to secure your web traffic, okay, HTTP connections. So when you see, let's say, a URL of https://, you're using HTTP, but on the default TCP port 443 with an extra layer of encryption and authentication between HTTP and layer 4 TCP. This was designed by Netscape, and it provides authentication and encrypted communication on World Wide Web traffic. It's not really a separate protocol, but it just combines normal web interaction over an encrypted secure sockets layer, or more recently and more commonly, a TLS security connection. So when you see HTTPS, just think of web traffic with SSL or TLS. So it really works hand in hand with our first bullet point here. Now, SHTTP is an alternative technology to our HTTPS. It's still used to encrypt web communications carried over HTTP. It's used for sensitive transactions like internet e-commerce or other online web transfers. The problem is it's not really used that often, okay? CompTIA wants you to know about it. It is an alternative, but because of the fact that Netscape and Microsoft have supported HTTPS historically with SSL and TLS, SHTTP has pretty much fallen by the wayside. L2TP is the Layer 2 transport protocol, which obviously should lead us to believe that it does virtual private network tunneling at Layer 2. This particular protocol was born out of Cisco's Layer 2 forwarding as well as Microsoft's point-to-point tunneling protocol. There's actually a new version of this called L2TP version 3, which is a proposed standard that adds additional security, improved encapsulation, and the ability to transfer data links other than simply PPP over an IP network. The familiar things like frame relay, Ethernet, and ATM. L2TP performs like an OSI Layer 2 protocol for tunneling network traffic between two endpoints over untrusted networks like the Internet. That's how it acts, but in fact, it's actually a Layer 5 session layer protocol, and it uses UDP, User Datagram Protocol, port 1701. It's very common to carry PPP sessions inside an L2TP tunnel. It doesn't provide confidentiality or strong authentication on its own. It's really a tunneling protocol. But typically L2TP is combined with IPsec or IP security to secure the L2TP packets. So it's basically L2TP does the tunneling, IPsec provides the confidentiality, authentication, and integrity. IPsec is the Internet Protocol Security, and it's really a framework. It's a suite of protocols to secure IP communications by authenticating and or encrypting each IP packet in the data stream. IPsec also provides cryptographic key establishment as well, which is why you'll see it used in a public key infrastructure. Now, remember, Layer 2 TP acts like Layer 2, but operates at session Layer 5 of the OSI model. IPsec is a Layer 3 protocol, the network layer of the OSI model. And it's different than SSL and TLS and SSH down here because these operate at transport layer 4 through 7 application layer. They operate higher. IPsec is operating at layer 3, so it's more flexible. It can be used to protect layer 4 protocols that include both TCP and UDP, which are the most commonly implemented transport layer protocols. Also, IPsec is superior over SSL or TLS because the applications don't have to be designed to use IPsec. Okay? If the application is using SSL or TLS, it has to be designed into the actual application itself. So IPsec is a more open framework of standards that provides confidentiality, data integrity, and data authentication between the peers. It uses the IKE protocol, the Internet Key Exchange Protocol, to handle the negotiation between the two peers. It negotiates the protocols and algorithms based on security associations and policies. So in a nutshell, IPsec is a framework. It's a set of cryptographic protocols and mechanisms that secure the packet flow, provide for mutual authentication, and establishes cryptographic parameters. Secure Shell or SSH is a network protocol that creates a secure channel to exchange data between two devices on a network. It was originally used primarily on Unix systems and Linux systems to securely access the shell accounts, but it's been designed and implemented as a replacement for the insecure Telnet. Telnet, which sends traffic in clear text or in plain text. There's also other insecure remote shells as well that Secure Shell can replace. It uses public key cryptography to authenticate the remote computer and let the remote computer, if it wants to, optionally authenticate the user. The Secure Shell server by default is going to listen on standard port 22. And it's used for a wide variety of reasons, really more than we can talk about here in this particular nugget. But it can secure FTP, file transfer, it can secure synchronization, it can be used in combination with SCP for a secure alternative to RCP file transfers, it's for secure shell login. It's typically used a lot to access networking devices to secure the management channels as well. It can be a full-fledged virtual private network as you connect, let's say, using PuTTY or Teraterm to a networking device. You create kind of a virtual private network tunnel between the management station and the device. Well, in part 2 of the cryptography domain of the Security Plus series, we looked at cryptography algorithms and protocols, talked about hashing concepts and related protocols, looked at encryption algorithms. We also talked about additional protocols that use cryptography: SSL, TLS, SMIME, point-to-point tunneling protocol, HTTPS and SHTTP, L2TP, IPsec, and Secure Shell. I hope this CB Nugget has been informative for you. I want to thank you for viewing. We'll see you in Public Key Infrastructure coming up next.